this part of Chapter 1, we're going to be focusing on bonding and on structures. So first I want to review ionic bonds. Remember, ionic bonds when atoms will lose or gain electrons to have a full outermost or valence shell. The reason atoms will gain or lose electrons is due to very large differences in electronegativity. So remember, electronegativity is the ability of an atom to attract electrons to itself within a bond. So when we have very, very large differences in electronegativity, the electrons are actually transferred from one atom to another. Our trend in electronegativity, if you were looking at your periodic table, our most electronegative atom is fluorine. They're on the top right-hand side of your periodic table. The least electronegative atom would be down on the bottom left-hand side of your periodic table, things like cesium and rubidium. The most electronegative atom on our periodic table is going to be fluorine, followed closely by oxygen, nitrogen, and then chlorine. For me, we're not going to do any actual calculations with electronegativities, but you should be aware of this trend to help us be able to predict reactivity. With our ionic bonds, the ionic bond, these ions that we are generating are actually held together by the electrostatic attraction. And the bond itself is that electrostatic attraction holding the positive and the negative together, or the anion and the cation. Our ionic structures form very large lattice structures. We cannot talk about ionic compounds in the form of a molecule because there are no individual molecules. We have this very large structure where the positives and the negatives are all attracted to each other. With ionic bonds, we do have a type of species that you do want to be familiar with, and this is going to be our polyatomic ions. Our polyatomic ions are ions that contain more than one atom that is covalently bound together. So this unit overall has a net charge. So an example of this would be something like ammonium, NH4+. This is a polyatomic ion. It is an ion, it has a +1 charge, but it contains 5 atoms, 1 nitrogen and 4 hydrogens. Those 5 atoms are all covalently bound together, so I'm going to connect them all with covalent bonds. And then as a whole, this has a net charge associated with it. We're going to be dealing some with polyatomic ions as we go throughout this chapter, so you do want to remember that we can have ions that are of more than just one atom. Next, I want to review covalent bonds. Covalent bonds are the sharing of valence electrons to have full valence shell. So this time, instead of losing or gaining, the atoms are going to share those electrons. The number of bonds that an atom can form depends on how many electrons is needed to reach the full valence shell. So with our atoms here in period 1 and in period 2, we can actually quickly define the number of bonds they will typically form in order to have those full valence shells. So hydrogen has 1 valence electron. It only needs 1 more to have a full valence shell. So hydrogen will form 1 covalent bond. We've already talked about carbon. Carbon can form 4 covalent bonds. It has 4 valence electrons and needs 4 more to have a full valence shell, so it will form 4 bonds. Nitrogen has 5 valence electrons, so it will form 3 covalent bonds to have a full outermost shell. Oxygen has 6 valence electrons, so it will form 2 covalent bonds. And our halogens have 7 valence electrons, so they will form 1 covalent bond. This is something you'll want to quickly be able to determine and remember so that you can quickly draw structures using covalent bonds. With covalent bonds, we also have our valence bond theory. Valence bond theory tells us that singly occupied orbitals on one atom are going to overlap singly occupied orbitals on another atom. And this is actually what comprises the sharing of electrons, or how atoms will share electrons. It's through an overlap of those atomic orbitals that we talked about in the previous slideshow. So if we actually look at this in terms of hydrogen, which is our simplest structure, for hydrogen, 1 hydrogen atom has 1 valence electron. A second hydrogen atom would also only have 1 electron. So as individual atoms, each one of them has an incomplete valence shell. So what we're going to see happen with valence bond theory is these 2 hydrogen atoms will come close enough together that we actually see an overlap of their orbitals so that they are actually sharing the electrons between them. So I've tried to kind of put those two arrows together in that overlap area of our two atoms. This is what valence bond theory defines for us. With this, we can talk about it in terms of energy as well, that this overlap actually gives us a lower energy than if the two atoms were separate. So in the diagram here, we're going to define our 0 point as when the two atoms are completely separate from each other. As my atoms get closer and closer together and they start to overlap, we actually see a decrease in energy until we hit the point where the two atoms are overlapped and they are sharing those electrons. This is what we refer to as in two atoms being bound together. So we're going to define this as being our bond. And there's an ideal bond length that is associated with this distance and the amount of overlap that we have. And each atom combination of two atoms will actually have an ideal bond length associated with it, which is related to how close those nuclei are together and how much those orbitals will overlap to each other. If I continue to push the atoms closer together and form more of an overlap, we actually start to see an increase in our energy. So over here I might have my two atoms very, very close together, and it's almost like they are too close. And the two nuclei are too close to each other that those positive charges are starting to repel each other. So we see a high increase in energy if we try to push our atoms any closer than that ideal distance between them. This energy difference here between when they are separated and when they are at that ideal distance, this is how we calculate our actual bond energy. And if you remember in our previous slide, we talked about the bond energy relationships between carbon-carbon compared to silicon-silicon, and this is how we would be looking at that bond energy. So the larger bond energy that we have, the more stable those bonds are because the lower in energy they actually are when we see the bond compared to them being farther apart from each other. And most of chemistry is trying to get to the lowest energy state that we possibly can. So we like to have atoms bound together to have those full valence shells, versus having individual atoms that have incomplete valence shells. Just to give you some information with this hydrogen-hydrogen relationship, the ideal bond length for hydrogen-hydrogen is going to be 74 picometers. And the energy here is about 436 kilojoules per mole for the bond energy. I'm never going to make you regurgitate any of those numbers, but I'd like to give them to you throughout the slides, just so that you've got some things that you can compare back to look at some relationships. But I don't expect you to memorize any of these values. So with valence bond theory, what we just looked at here was what we call a single bond. One pair of electrons is going to be shared between the two atoms through the overlap of those orbitals. We can also have those double bonds, which is where we're going to share two pairs of electrons between two atoms, which means we have to overlap more orbitals. We could also have triple bonds, where we're going to share three pairs of electrons, where once again we will have to overlap even more orbitals in order to share that number of electrons between the two atoms. As we go from a single bond to a double bond to a triple bond, so as we would go down this column, we're going to see bond energy increase. So the largest bond energy, or the lowest energy standpoint, so the largest bond energy is going to be the triple bond compared to the single bond. We're also going to see changes in bond lengths as well. So as we go from our single bond to our double bond to our triple bond, we are going to see our bond lengths decrease. So the shortest bond out of these three is going to be the triple bond. The longest bond would be the single bond. And you'll see that there's this nice inverse relationship between bond length and bond energy. The shorter the bond length, the higher the bond energy will be. So the stronger that bond really is for us if we look at it in terms of strength. So the next thing we want to quickly review are going to be Lewis structures. So our Lewis structures are what shows us really how atoms are connected. We looked at a Lewis structure back with ammonium, that NH4+ polyatomic ion. So these Lewis structures literally show us how all the atoms are going to be connected together. They are only going to show valence electrons, so we're only really going to care about the valence electrons. Those are the ones used in bonding. So those are the only ones that we're going to show in our Lewis structures. We can actually look at drawing Lewis symbols for all of our atoms. In those Lewis symbols, they're notations, they're symbols that show us the elements. symbol and then how many valence electrons it has. So if we were to look at the Lewis symbol for carbon, I would draw my symbol for carbon. Carbon has 4 valence electrons, so I would draw dots to represent those electrons around carbon. We treat each symbol like a box, so it has 4 sides, and we're going to follow Hund's rule. We're going to treat each side as if it is degenerate equivalent. So I'm going to put 1 dot on each side, and then I'm going to go back and pair. This is going to help me be able to pair electrons appropriately and have the correct number of bonding patterns when I draw my Lewis structures. So if we look at one of our halogens, like fluorine, that had 7 valence electrons, if we look at this, I would go through and I would put 7 dots around my fluorine. It doesn't matter what side the unpaired electron is on our box. What matters is the number that we have, that I should have 3 pairs of electrons around fluorine, and I should have 1 unpaired electron or dot around fluorine. Lewis structures are also going to show bonding and non-bonding electrons. Bonding electrons are going to be electrons that are shared between the 2 atoms. So bonding electrons can be single bonds, which we would just represent with a single line. They could be double bonds, which we would represent with 2 lines. They could be triple bonds, which we would once again represent with 3 lines. So those would be our bonding electrons. But it is also going to show those non-bonding electrons. Non-bonding electrons are typically what we call lone pairs. So these are going to be pairs of electrons that are not in between 2 atoms. And we do want to get in the habit of showing these. So if we look back at fluorine, if this were part of a structure, fluorine would have 3 non-bonding electron pairs, or 3 lone pairs of electrons. And we want to get in the habit of showing those in our Lewis structures because they can play a very large role in reactivity of our molecules. We can also have free radicals as non-bonding electrons. A free radical is just an individual unpaired electron around an individual atom. We are not going to focus too much on radicals. I will always tell you if we're going to be dealing with a radical, but you do want to recognize that radicals do exist, and they are very reactive species, and we can show them in our Lewis structures. Typically in our Lewis structures, we are going to be following the octet rule, which is kind of what our focus has been. Carbon has to follow the octet rule, so typically we're going to be looking at things that do not violate the octet rule. The octet rule tells us that each one of our atoms have to have 8 electrons around it in order to be stable. So let's just quickly review some steps on how to draw Lewis structures. If you're already very comfortable with drawing Lewis structures, you can kind of skip ahead and just practice drawing Lewis structures. For those of you that have forgotten how to draw Lewis structures, I want to quickly go through just some steps to help you be able to draw them. The first thing we have to do is count up the total number of valence electrons in our structure. So that means I'm going to look at the atoms that I have, how many of each of those atoms, and I'm going to count up all the valence electrons that are within that structure. From there, I'm going to add an electron for each negative charge. If I'm dealing with a polyatomic ion, I'm going to subtract an electron for each positive charge if I'm dealing with a polyatomic ion. So we can adjust those electron counts if we're dealing with charged particles. From there, I'm going to connect all my atoms via a single bond to a central atom. The central atom is usually the atom that can form the most bonds. So for us, it will typically be carbon. And it is typically also the least electronegative as well. So if you have a couple options, your goal is to go with the least electronegative. So remember that trend that we looked at from our periodic table on electronegativity. A lot of our organic compounds are going to have more than one central atom, so we'll be looking at some of those scenarios as well. But for right now, your goal should be focusing on one central atom and connecting everything to that one central atom. Once I have everything connected via single bonds to that central atom, I'm going to distribute electrons as lone pairs to satisfy the octet on all of the atoms that I have. So right now my goal is just to go in and put a whole bunch of pairs. Remember the octet is 8, so I want to make sure that each of the atoms have 8 electrons around it. Then I'm going to check my electron count on the structure that I have drawn, so how many total electrons I have put in, to the count that we did back in step number 1. If they match, I'm probably done and I probably have the correct Lewis structure. If the two do not match, I have to go back and I have to use multiple bonds. I have to somehow get rid of electrons or add more electrons in. Typically it's getting rid of electrons. And we do that by using multiple bonds instead of single bonds between our atoms, and then adjusting the number of lone pair of electrons that we have. What I want you to notice is this idea of drawing Lewis structures, it is a trial and error process. we try something, we see if it works. If it doesn't, we go back and we try something different. The more you practice with Lewis structures, and probably what you learned in your freshman class, the more you practice, the easier it became, because you learned some tricks of the trade and some ways that atoms actually behave in their structures. There are some exceptions to the octet rule that I do want you to be familiar with. One of the exceptions is when we can have less than an octet. The two that you need to know for me are going to be boron and aluminum. Boron and aluminum had 6 electrons total around them, not 8, and they are in their most stable form. So boron and aluminum, we're not going to see 8 electrons around them to be stable. We're only going to see 6 electrons in total around them to be stable. We can also have expanded octets. We refer to these as hypervalent central atoms, and these will be the central atoms that are that violate the octet rule. It would not be the outer atoms. And anything that is in period 3 or lower, so things like phosphorus and chlorine, if they are the central atom, they can be hypervalent. They can have more than 8 electrons around them to put them in their most stable form. So let's look at a couple of examples, some simple examples from your freshman level course. So the first one is going to be NH3. For NH3, the first thing I need to do is tally up all of my valence electrons. So for nitrogen, nitrogen has 5 valence electrons. Hydrogen has 1 valence electron, and I have 3 of them in total. So the total number of electrons I can have in my structure is going to be 8. For this, the central atom is going to be the one that can form the most bonds. Nitrogen can form 3 bonds. Hydrogen can only form 1. So my central atom becomes nitrogen, and I'm going to connect the other atoms to it just via a single bond. I'm then going to go back and put in my lone pairs to make sure everything has an octet. So remember, hydrogens are never going to follow the octet rule. They only have the 1s subshell, so they're never going to have lone pairs around them. So hydrogen is already satisfied. So I'm going to go in, and my nitrogen needs 2 more electrons in order to have an octet around it. So now I'm going to count up all of my electrons. So for this, I have a total of 2, 4, 6, and then 7, 8 with my lone pair of electrons, which matches the count that I had from the beginning. So we are done with our Lewis structure. So nitrogen is the central atom, and I've got 3 single bonds to nitrogen and 1 lone pair. So let's look at an example of CCl4. So if we actually walk through our electron count on this one, carbon has 4, chlorine has 7, and I have 4 of them. So my total electron count should be 32 electrons. Carbon will once again be my central atom. It can form 4 bonds. I will connect each one of my chlorine atoms to it. Then I will go through and make sure everything has an octet by putting in my lone pairs, which means each one of my chlorines needs 3 lone pairs or 6 total electrons around it. So now I'm going to go through and I'm going to do my electron count. So each one of my chlorine has 8 electrons. So if we count them, I've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, and that matches. So everything has an octet. So my final structure, just to write it one more time nice and clean, would be the carbon is the central atom, and each one of those chlorines has 3 electron pairs associated with it. So let's look at one last example. This would be POCl3. So to do my electron count, phosphorus has 5, oxygen has 6, chlorine has 7, and I have a total of 3 of those. So my total electron count once again is going to be 32. In this example, phosphorus becomes my central atom. It can form the most bonds, 3 bonds. Oxygen can only form 2, chlorine can only form 1, so phosphorus becomes my central atom. From here, following my rules, we're going to connect everything with a single bond. And then I'm going to go ahead and give everything an octet around it. And then I'm going to do my electron count. So I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, and 32. And everything has a nice octet associated with it. But one of the things that we're going to talk about later on is we also need to talk about how things are bound together as well. So these were some very simple steps to actually look at things. But one of the things I want you to go back and think about, even though we have this structure of phosphorus as our central atom and single bonds to all of our atoms, so there's our structure nice and cleaned up. I want you to think back about what our Lewis symbols look like. Because one of the things that we said about oxygen is oxygen only had 6 valence electrons associated with it. And if we look at the structure that we have drawn here, we have oxygen with lone pairs and then a bond, which really shows that it would have 7 valence electrons associated with it. So even though this follows those steps, this is actually not the best structure that we could truly draw for our POCl3 because of the number of valence electrons that each one of those atoms has. And it's something that we're going to have to go back and we're going to think about. And I'm going to give you some rules here in a couple of slides to start thinking about some of these as well. So because of that, this is not the best structure that we could draw for POCl3, but it is going to be one of the structures that we could draw for POCl3. The best structure that we could draw for POCl3 is still going to follow all of these rules and guidelines, but it's going to go back to the idea that oxygen should form 2 bonds as well. So a more valid structure that we would have for POCl3 is going to have a double bond between oxygen and phosphorus, and then single bonds between the phosphorus and the chlorines. This structure, if you go through and you actually do your electron count as well, still has 32 electrons. It still follows all of our rules and our guidelines. But it's a more valid structure or a better structure for us because of the way that we have dealt with the oxygen and oxygen forming 2 bonds compared to the oxygen just forming 1 bond. So you do have to pay very close attention. Those rules and those steps that I gave you, they're a guideline, they're a guide frame, but you do want to make sure that you are checking to make sure that things make sense chemically with the number of bonds that we have already defined that most atoms will form. So with our Lewis structures and having these covalent bonds within our structures, we do have to talk about polar covalent bonds. Because when we talk about the sharing of electrons, not all electrons are going to be shared equally between the 2 atoms. And what we're going to see is that the electrons are once again going to be more attracted to the electronegative atom within the bond than the less electronegative atom. We're not going to see so much of a difference since we're sharing the electrons that it becomes ionic, but we will see some discrepancies there. What we are going to see is a bond dipole being formed. And this is the separation of a partial positive and a partial negative charge. So we're still sharing the electrons, which is why we don't see an ionic separation, but we do still see a separation of charges because the electrons, the negatively charged particles, are going closer to one atom than the other, which is causing this charge separation, this bond dipole. So we have a couple of notations that you do want to be familiar with our bond dipole. So if I just look at an individual bond, let's look at a bond between carbon and oxygen. So we've already talked about the oxygen is much more electronegative than what carbon would be. Oxygen is one of our most electronegative atoms. So the electrons here would not be shared equally. The electrons would be closer, they'd be held tighter by the oxygen than by the carbon. So we would say that the oxygen has a partial negative charge and the carbon has a partial positive charge. And we would denote this by using these deltas, a lowercase delta negative for the partial negative charge, a lowercase delta positive for the partial positive charge. Another way that we could look at this is also to have a line drawn. We can draw a line with an arrow as well. The arrow kind of dictates where the electrons are going. So in this, the electrons are going towards the oxygen, so that would be my partial negative area. And you'll notice that the tail of the electron has a little positive sign on it, and it would be over the partial positive atom. So this is one of the dipoles that we will see in organic chemistry. Another one is going to be with metals, so we are going to see some bonds between carbons and metals. But in this scenario, based on our electronegativity trends, carbon is now more electronegative than the metal, the lithium. So in this scenario, my carbon would be partially negative and my lithium would be partially positive. If we look at it with the arrow notation, my arrow would now point towards carbon with the tail of the arrow over lithium. So you do want to be familiar with that electronegativity trend so that you can do this type of bond dipole prediction. We can then take this entire bond dipole and we can put it in the context of a molecule. So this CO bond we oftentimes will see in methanol. Our structure for methanol has a carbon bound to an oxygen. That oxygen is also bound to a hydrogen and has 2 lone pairs. The carbon is then bound to 3 other hydrogens as well. So we do have some polar bonds here. We do have a nice polar bond between the carbon and the oxygen, so I'm just going to draw on my little line. And we also have a very polar bond between the oxygen and the hydrogen as well. So I'm going to draw on my bond dipole. So what we're going to see here is these arrows are pointing towards where the most electron-rich area will be. The most electron-rich area in this structure is going to be our oxygen atom. Electron-rich areas are oftentimes going to be denoted in red for us, which is why I've denoted it in red for you as well. These would be electron-rich areas, so they'd be partially negative areas that we have. You'll notice that we have electrons being pulled away from other areas as well. So over here by the carbon would be an electron poor area. This hydrogen over here would be an electron poor area. Those are oftentimes denoted in blue for us as an area. And these would be our partially positive areas, areas where we don't have a lot of electron density. We can see the same thing with our lithium. An example of this is what we would refer to as methyl lithium. So with this one, I would have my carbon connected to my lithium. And then that carbon would also be attached to 3 other hydrogens as well. Remember, carbon needs to form 4 bonds. But with this, if we look at the bond dipole, it would be going away from the lithium and pointing towards the carbon. So here my carbon area would be my electron-rich area. My lithium area would be my electron-poor area. So we're going to use these bond dipoles to help us predict reactivity in future chapters by knowing where these electron-rich areas are and where these electron-poor areas are. Once again, based on the electronegativity trends that we see in atoms from our periodic table. From here, I want to talk a little bit about formal charges and oxidation states. These are really electronic ways of bookkeeping that will help us predict if we have the best structures or the most valid structures drawn for our Lewis structures by looking at formal charges and oxidation states. We will also use these values, these formal charges and oxidation states, to help us predict reactivity as well. So first, to define formal charge. The formal charge is in a covalent bond, half of the electrons are going to be assigned to each atom. So when we calculate our formal charges, we are going to assume equal sharing of electrons as we get ready to do our calculation. The formula that we're going to be using for formal charge, I'm going to abbreviate formal charge FC. So the formal charge is going to be equal to the number of valence electrons in the atom. I'm going to continue to abbreviate valence electrons VE. And this number is what we're going to get straight from the periodic table. It's what you would use to determine your valence electron count when you were doing your Lewis structure. From that, I'm going to subtract the number of bonding electrons. And I'm going to divide it by 2. So remember, within the bonding electrons, we have 2 of them, and we're going to split them equally. Half are going to be assigned to each atom, which is why we're dividing the number of bonding electrons by 2. And then from that, we're also going to subtract the number of non-bonding electrons. And remember, these are going to be the lone pairs that we have. So this is how you will calculate the formal charge, and you're going to calculate the formal charge for each atom within the molecule. Some of the guidelines that we have is the sum of the formal charge on all the atoms in the molecule is going to equal the charge on the species. So if it is a neutral molecule, all of our formal charges have to add up to 0. If we're dealing with a polyatomic ion, all the formal charges are going to add up to that ion charge. We're going to use formal charges to once again to help us predict reactivity. So we'll be using formal charges quite often. So this is a calculation you want to be able to do fairly quickly as we go throughout the semester so that you can help predict reactivity later on. We are going to show formal charges in our Lewis structure, and I'll show you how we will show those formal charges in our Lewis structures as we get ready to draw them. So now let's talk about oxidation states. It's another way that we can do the same type of electronic bookkeeping, but the way we calculate them is going to be very, very different. Oxidation states is in a covalent bond, the electrons are assigned to the more electronegative atom. So we're going to assume ionic character. So remember, for formal charges, we assumed everything was shared equally. In oxidation states, we're going to assume ionic character. We're going to assume that the electrons are transferred in everything. If in the bond the two atoms are identical, then we will split those electrons evenly. One goes to one atom, one goes to the other. But again, that is only if the atoms are identical to each other. So for our oxidation states, and I'm just going to abbreviate oxidation states OS, there really isn't a calculation. What you're going to be doing is you're going to be comparing the number of electrons in your molecule compared to the number of electrons from the periodic table once again. So if we have more electrons assigned in our molecule than what it would have straight from our periodic table, we have a negative oxidation state. So if we have 2 extra electrons assigned, we would say we have an oxidation state of -2. If we have 3 extra electrons assigned, we would have a -3 oxidation state. If we have fewer electrons assigned in the molecule, we have a positive oxidation state. And again, it's going to be based off of how many. If we have 3 fewer, it will be positive. If we have 1 fewer, it would be +1. Once again, though, the sum on all the oxidation states of all the atoms in the molecule, once again, has to be equal to the charge in the species. So if we are having a neutral compound, all of our oxidation states should add up to 0. If we have a polyatomic ion, we have a +1 charge, all of my oxidation states should add up to +1. So let's look at an example. The example that we're going to look at, we're going to have a carbon atom that is going to be attached to 3 hydrogen atoms. We're going to attach it to a nitrogen. That nitrogen will be attached to 2 hydrogen atoms and also 1 oxygen. That oxygen atom is going to have 3 lone pairs. So the first thing we want to be able to do is we want to be able to assign oxidation states and formal charges. So the first one that I'm going to look at is I'm going to look at the hydrogens. So you'll notice every single hydrogen in this structure is equivalent. They all have 1 covalent bond associated with them. So if I first calculate my formal charges, so the formal charge on my hydrogen naturally has 1 valence electron from my periodic table. In my structure, all of them are the same, so I'm just going to focus on one of them. It has 2 bonding pairs of electrons because it has 1 bond associated with it, which I'm going to divide by 2. And it has 0 lone pairs. So if I actually do my calculation, each one of those hydrogens has a formal charge of 0. So again, the number of atoms that we have minus 1/2 the number of bonding minus the number of lone pairs. So for hydrogen, it is equal to 0. So now let's look at carbon, and I'll do carbon in red. So the formal charge on carbon, if we look at carbon on the periodic table, carbon has a formal charge of 4. If we look at it in my structure, it has 2, 4, 6, 8 bonding electrons, which I'm going to divide by 2, and it does not have any lone pairs. So the formal charge on carbon is also going to be 0. So next, let's look at nitrogen. The formal charge on nitrogen, nitrogen has 5 valence electrons. In my structure, it has 2, 4, 6, 8 bonding electrons, which we'll divide by 2, and it does not have any lone pairs. So the formal charge on nitrogen here is going to be a +1. Lastly, let's look at oxygen. So my formal charge on oxygen, oxygen has 6 valence electrons from the periodic table. In my structure, it only has 2 bonding electrons divided by 2, and then it has 2, 4, 6 lone pairs. So the formal charge that I have on oxygen is going to be a -1. So right now this is a neutral molecule as I have it drawn, and you will see that all of my oxidation states would add up to 0 as well. So that is how we would go about calculating formal charges. So from here, let's use the same molecule, but let's look at oxidation states. So the oxidation states of hydrogen. If we look at our structure in hydrogen, remember now we're going to be looking at complete transfer of electrons. So if I look at my hydrogens that are bound to carbon, carbon is more electronegative. So all the electrons are going to go towards carbon from my hydrogen. I see the same thing with hydrogen and nitrogen. All of the electrons are going to go towards nitrogen. Nitrogen is more electronegative. So in my structure, oxygen has 0 electrons assigned to it. If we actually look at hydrogen on the periodic table, hydrogen has 1 electron associated with it. So this is 1 less than what it should have based on our periodic table. So my oxidation state is going to be a +1. And it will be a +1 for all of the hydrogen atoms. So next, let's talk about the oxidation state of carbon. So if we look at carbon, carbon is more electronegative than hydrogen, so it's going to pull all those electrons from it. But carbon is going to be less electronegative than nitrogen, so those electrons are going to go towards nitrogen in that carbon-nitrogen bond. So in this structure, carbon has 6 electrons assigned to it. It has 2 electrons from each of the hydrogens that it is bound to. But on the periodic table, carbon should have 4 valence electrons. So in my structure, carbon has 2 more electrons than what it would have normally as an atom. So it would have a -2 oxidation state. Next, let's look at the oxidation state of nitrogen. So in nitrogen, once again, it's going to pull the electrons from carbon. It's going to pull the electrons from the hydrogen. But with oxygen, oxygen is more electronegative than the nitrogen, so oxygen is going to get the electrons in that bond. So in my structure, nitrogen also has 6 electrons assigned to it, 2 from carbon and 2 from each of the hydrogens. Nitrogen should normally have 5 valence electrons, so this has 1 more electron than what it should have naturally, so this is going to have a -1 oxidation state. Lastly, let's look at oxygen. Oxygen is the most electronegative, so it's going to pull those electrons from the nitrogen, and then it also has 3 lone pairs, so it has a total of 8 electrons assigned to it in our structure. It should normally have 6, so this is 2 more than what it would normally have, which gives us a -2 oxidation state. So now that we have all of our oxidation states assigned, they should add up to 0. But don't forget, with the hydrogens, we have a total of 5 hydrogens in our structure. So we have 5 of those +1s. So the overall oxidation states also add up to 0, which they should since we have a neutral molecule. So you want to make sure that you can calculate both formal charges and you can calculate oxidation states for any of our molecules. The next thing I want to talk about is going to be resonance theory. So remember that we had where we could draw multiple different structures that followed our rules for the POCl3. What we were talking about then and what we were looking at is what resonance theory follows for us. So I want to go over some rules associated with resonance structures. And this is when we can draw species with 2 or more Lewis structures that follow all of our guidelines of octet rules, etc. These are referred to as resonance structures, the individual Lewis structures that we can draw for a molecule that would follow our rules and our guidelines for that structure. What's going to differ in these resonance structures is the placement of valence electrons, such as multiple bonds and lone pair of electrons, not the actual bonding order of the atoms. So if you think back to our POCl3 structure, the only thing that differed between them was the double bond compared to the single bond between phosphorus and oxygen, and the number of lone pairs that we had on our oxygen atom. So that's all that resonance structures can differ by, is going to be the placement of the valence electrons, double bonds and lone pairs, not how the atoms are actually connected to each other in terms of the bonding pattern. With our resonance theory, resonance structures are imaginary. There's not an actual structure that looks like either one of the resonance structures that we draw on paper. Remember, we're drawing on paper what we think things should look like. The true structure in nature that we have would be represented by what we call a resonance hybrid. The resonance hybrid is a combination of all of the resonance structures that we have. It's a weighted average. So the resonance hybrid is going to look most like the lowest energy resonance structure, which is why we want to be able to draw the best structure. That best structure is going to look the most like the resonance hybrid that we would have in nature. So it's typically our job to draw the better structure, to draw the best structure based on formal charges and based on oxidation states. The best structure is going to have the greater number of atoms with filled valence shells. So when we start looking at all the different resonance structures, the best one is going to be the one with the most number of atoms with filled valence shells. It's going to have the largest number of covalent bonds, so we'd rather see bonding. Remember, bonding is lower energy. We'd rather see bonding than lone pairs. It's also going to be the structure with the fewest atoms with formal charges. Our goal is to really get formal charges equal to 0 if we can. Resonance provides stability. So one of the things that we're going to see with resonance theory is that the more resonance structures we have, the more stable that molecule is. Electrons are delocalized over multiple atoms when we talk about our resonance structure and our resonance hybrid. So that destabilization or delocalization is actually stabilizing when we start looking at the resonance hybrid compared to the individual structures that we have. Resonance stabilization is going to be very, very large when resonance structures are equivalent. So if we look at our resonance structures and they're all weighted the same, one is not better than the other. This is when we're going to see the largest type of resonance stabilization associated with that structure, with that molecule. If all else is equal in terms of the number of resonance structures that we have, the equivalency of those resonance structures, the more resonance structures we can draw, the more stable the that structure is. So the greater number of resonance structures that we can draw on paper, typically the more stable that molecule that we are going to see. So based on those rules, I do want to give you an example about what I'm talking about with resonance structures and how we can actually draw them. So I'm going to look at an example here with carbon. We're going to have 3 carbons in a row, and the last carbon in our chain is going to be connected to 2 oxygen atoms. If we go through and do our formal charge count, this oxygen atom out here with 3 lone pairs and only 1 bond has a negative formal charge. The double bound oxygen with 2 lone pairs has a neutral formal charge. Each one of our carbons is going to be connected to enough hydrogens so that each one of them has 4 bonds and therefore no formal charges associated with them. So this would be one way that I could draw this structure. This is what we would refer to as a resonance structure. But another way that I can draw this same exact structure, because those 2 oxygens are equivalent, I can also do it this way as well. And instead of having the negative formal charge on the oxygen atom that is lower in my structure, I can actually put it on the one that is going up in my structure as well. So the only thing that I have really changed is the number of electrons on one of the oxygen atoms and the type of bonding between those 2 oxygen atoms as well. So this is a resonance structure as well. Both of these are resonance structures of the same molecule. The way that I would demonstrate that on paper is that these both represent the same thing, is I would use a resonance arrow. A resonance arrow is a double-sided arrow, and basically it tells me that these 2 structures don't exist by themselves in nature. They exist together as a resonance hybrid. Typically, I would then also put both of them in square brackets so that they become one unit for us. So one of the things that you're going to see is we literally just move the placement of the double bond and the lone pair of electrons. One of the things we're going to start looking at in organic chemistry is we want to be able to define the electron flow. The way that we look at the electron flow is we're going to describe it in what we call a mechanism. And that mechanism is going to define where the electron started, and it's going to tell me where the electrons end up. And we're going to use arrows to denote those resonance structures or this resonance flow, this mechanism. So all I'm doing in my structure is I'm going to take one of my lone pair of electrons, and it is going to come in and it is going to form the new double bond between that oxygen and that carbon atom. What you want to notice is my resonance arrows start where the electrons are, and it points to where those electrons are going. At the same time I'm forming that new double bond, I have to break a bond because carbon can only have 4 bonds. So one of the pairs of electrons that is on this oxygen making the double bond, it is going to go to become the lone pair of electrons on that new oxygen atom as well. So my arrow is going to start with one of the pairs of electrons, the bonds, and it's going to go to form a new pair of electrons on the top of that oxygen atom. These are my mechanistic arrows that show me how I converted from one resonance structure into the other resonance structure. We're going to get a lot of practice with resonance arrows, so you want to start now learning to write them and what they represent for you. But these two resonance structures actually generate, remember, our resonance hybrid, the true structure that we would see in nature. And what that means for us when we actually look at the structure in nature is that both of those oxygen atoms are equivalent. So what that means for us is, remember, we had different bond lengths. A single bond was longer than a double bond. And in my true structure, what I don't see is one short and one long. I see 2 CO bonds. So both of those CO bonds are identical in length. I don't see one short, one long. So one of the ways that we can denote that is I'm just going to use a little dashed line to say that both of those bonds are in between a single and a double bond. It's not as long as a single bond, but they are not as short as a double bond. They're probably what we would call a bond and a half in length, because those two resonance structures are averaged together, and neither one is better than the other. They're both equivalent in terms of formal charges, so we would have a bond length of 1.5. The other thing that we would see is going to be dealing with charges, that the charges on both oxygen atoms is going to be the same as well. So the way that we could denote that, we can do that in a couple of ways. I can have a delta negative on both of those to show that they would have some negative charge because of the equal distribution of the electrons between them. Or I might just put a big negative sign here in the middle to say that that negative charge is distributed with that dotted line between those two oxygen atoms. Either one of them would be appropriate, but what we need to recognize is that both of those oxygen atoms are bearing some negative formal charge because of how the bond is actually distributed between the two of them. So this structure that I drew down here is what we would refer to as the resonance hybrid. It is the average structure between the two resonance structures that we drew on paper. Resonance hybrids will contain partial bonds, and they will contain some partial charges as well, because we're averaging all those other structures together. So with some guidelines for drawing these resonance forms, because you will need to be able to get practice in drawing these resonance forms as we start through organic chemistry, and there's some things that you want to look for to know that you can potentially draw a resonance form. One of them are going to be 3 atom groups that you're going to be looking for. And within those 3 atom groups, what you are really looking for is you're looking for some multiple bonds and some single bonds. Where that little asterisk on that third atom is either going to be a vacant orbital, meaning it would have a positive formal charge, or it would be something like boron and aluminum that has a vacant orbital associated with it, or you would be looking for it to have a lone pair of electrons, like we saw on the previous example that we just walked through. If you see this type of scenario, we've got a 3 atom group with a double bond and then or multiple bond, and then we've got an atom with vacant orbitals or lone pairs, it should jump out that we can draw resonance structures. So the resonance structure that we would have for this one, we would change where that multiple bond is found, and then we would change where the lone pair or the vacant orbital is found as well. So you'd be looking for these 3 atom groups with multiple bonds and lone pairs or vacant orbitals between them. You'll notice we really didn't change anything on the Y, the middle atom. What really changed were those 2 outer atoms. We can also see the exact same thing with some 2 atom groups. With 2 atom groups, we're looking for, instead of multiple bonds, what we would be looking for is an atom with lone pairs, and then an atom with a vacant orbital, where that little asterisk this time only represents the vacant orbital. So what we can do with our resonance here is, because there is a vacant orbital, I can use those lone pairs to generate a multiple bond. So we can see some resonance between two atom groups if we have a lone pair beside a vacant orbital as well. So this is another way that we can look at some resonance forms. These two resonance forms are probably not going to be created equal. One of them will typically be better than the other one based on formal charges. We can also have our ring notation with alternating single and double bonds. This is very similar to 3, except we would have a complete ring notation. As we walk around our ring, we would see alternating single and double bonds. So those X's are just individual atoms. One of the ways then that we can draw this resonance structure is we just switch the alternating single and double bonds. So wherever there was a single bond, it becomes a double bond. Wherever there was a double bond, it becomes a single bond for us. And that is a resonance hybrid as well. So you'll see a lot of these rings. Again, with all of these, remember that the true resonance hybrid is a combination of both of those. So in these ring structures, oftentimes what you will see drawn instead of the alternating single and double bonds is you will just see the single bonds connecting all of the atoms, and then a ring will be drawn inside. And that ring tells you that we see resonance, that we have these alternating single and double bonds. But in reality, all of those bond distances are identical. They're somewhere between a bond and 2 bonds, about 1.5 bonds in length and energy as well. So that becomes the true resonance hybrid based on the individual resonance structures. With all of our structures, we do want to get to some shorthand notation that you do want to be familiar with. With our shorthand notation, it's really just because of ease of drawing. We're going to be drawing a lot of carbons, a lot of hydrogens, and we want to find ways to clean up our formulas. So what we have focused on right now in this chapter has been Lewis structures. In a Lewis structure, it shows us all of the atoms, and it shows us all of the connectivities. So I'm just going to show an example here where I'm going to take 4 carbon atoms, I'm going to connect them in a chain, I'm going to branch off 1 carbon atom off of 1 of the carbon atoms as well. So I have this nice branched structure, and this is what a Lewis structure would look like. Notice I'm showing you every single atom, I'm showing you every single bond, and they are long to draw, they take a lot of time, they take up a lot of paper, and if these structures get very, very large, which they will in organic chemistry, they can become very sloppy as well. So these are our Lewis structures. It's our fundamental idea. You want to be able to draw them. You should be able to draw them from your freshman class, but we want to find ways to clean them up and make them simpler and shorter to draw. So one of the ways that we can do that in organic chemistry is what we call condensed formulas. In a condensed formula, I'm not going to show you most of the bonds. So I'm going to say that I've got a CH3, and that is connected to a CH2. That CH2 is connected to a CH, which is bound to a CH3 that is branching off, and then another CH3 beside it. So this is one way that I can write a condensed formula. I'm not showing you all the bonds between all the carbons and all the hydrogens. I'm just showing you one of the branches. I can even get a little bit simpler in this, and I can say that I have a CH3 that is connected to a CH2. That CH2 is connected to a CH, but that CH is actually connected to 2 CH3s. So this time I'm not showing you any of the bonds. And you would have to put this together to work backwards to know what the actual structure is based on the number of bonds that carbon can form. So right now we want to be able to go back and forth between those Lewis structures and the condensed structures and know what each one of them represents. But these condensed structures and formulas can be a little bit confusing because we're not showing you any of the bonds. And it really, you almost have to draw them out sometimes to see how things are connected. So one of the things that we really get to in organic chemistry and you want to be able to focus on, and I would say within a week, you want to be able to really focus on line structures. Line structures give us the most amount of information from an organic standpoint that is useful for us as we're writing our organic reactions. With our line structures, what we're going to do is we're going to completely ignore atoms of carbon and hydrogen, and I'm not going to write them at all. Remember, in organic chemistry, that's mainly what we're dealing with, carbons and hydrogens. So I don't want to waste my time writing carbons and hydrogens. So the line structure for the structure that I have been drawing looks like this. It took me 2 seconds to draw, and I actually get all the same information that I did in a Lewis structure, and a little bit more information I did in my condensed structure. So the way that a line structure works is every point of a line becomes a carbon atom. So if we actually think about my points here, I've got carbon atom 1, carbon atom 2, carbon atom 3, carbon atom 4, and then I've got a carbon atom 5 down there. So I still have my 5 carbon atoms. Then I always have to remember carbon forms 4 bonds, which means any bond not shown is going to be a bond to a hydrogen. So this first carbon atom here has a total of 3 hydrogens on it because it only has 1 bond. My second carbon atom has a total of 2 hydrogens on it because there are only 2 bonds. This carbon atom here in the middle has 1 hydrogen because it already has 3 bonds shown, and each of these ones on the end have 3 hydrogen atoms because it only has 1 bond. So by drawing this quick line structure, I am drawing a lot less. It cleans up my structure a lot more. So your goal is really to be able to get into this type of line structure and be able to draw them and be able to understand what they represent. The quicker you can get into drawing these line structures, the easier organic chemistry is going to be for you. So I want to give you a couple of other examples of some line structures that contain atoms more than just hydrogen and oxygen. So here is a structure that contains an oxygen atom. It also contains a double bond. So one of the things that you want to think about with double bonds is how that impacts the number of hydrogen atoms associated with each one of the carbon atoms. The other thing that I want to point out is we draw all other atoms other than carbon and hydrogen. So notice I drew in the oxygen atom. If those atoms of oxygen, nitrogen, phosphorus, whatever other atoms they are, if they are bound to hydrogens, I am going to draw in that hydrogen. So notice I didn't just draw the oxygen. I'm also drawing the oxygen bound to the hydrogen that it is attached to. So if you have hydrogens on anything other than carbon, you need to draw those hydrogens in. So if we actually look at the formula for this structure, the formula is C6H10O. So please make sure you understand how to get from this line structure into the number of atoms that we actually have. So make sure you can find all 6 of the carbons, all 10 of the hydrogens, and that oxygen atom as well. To give you one more example, to make sure that you can count the total number of atoms that we have, here's another example that now contains nitrogen. Notice I have drawn in the hydrogens that are connected to the nitrogen. And I've also put in some lone pairs. Typically we are going to see some lone pairs, and I should have really drawn in 2 lone pairs on my oxygen atom as well. We want to get into the habit of drawing those lone pairs because again they are going to tell us a little bit about reactivity in the future. With this structure that I have just drawn, the formula here is going to be C4H11N. So once again, please make sure that you can find those 4 carbon atoms, the 11 hydrogen atoms, and the nitrogen atom as well.